All right, fellas, so in section 2, all right, there's still some exponents out there that we don't know how to deal with yet. All right, so this one's going to help us with all real number exponents. Okay, so we've worked with rationals, we've worked with integers. We're going to extend that to all real numbers. So the real numbers are all non-imaginary numbers. Okay, so we've got the set of numbers out here that has to do with I, right, all the imaginary numbers. Then everything else are real numbers, right? And the real numbers are split into two sections. Okay, we've got the rational numbers, the ones we talked about last time, okay, that can be written as a fraction, and the irrational numbers. And irrational numbers are just numbers that can't be written as a fraction. So for example, pi can't be reduced to a fraction. Yes, you're going to say like 22 over 7 or whatever, or 3.14, but those are just, those are rounded, okay? Like square root of 2, cube root of 4, okay? Lots of roots, okay? E, if you've dealt with that before. Right, all those would be irrational numbers that cannot be written as a fraction, right, without rounding. So the rational numbers plus the irrational numbers create the real numbers. Right? We're going to be working basically with roots and pies in our exponents now. All right, and the other thing we're going to do is we're going to talk about exponential functions. All right, so that's really quickly I'm going to explain how the graphs of these functions look. Okay, so this is y equals b to the x power. Right, but b has to be some constant bigger than 0. Okay, so if b is bigger than 1, right, if something bigger than 1, you're going to have exponential growth. It's going to look something like that. Okay, it's going to grow real big. It's never going to go less than 0. Okay, and if you have b between 0 and 1, some fraction is going to be exponential decay, so it's going to be going the opposite direction. It's going to look something like that. It's going to get real small real quick. Okay. The other thing to know about these is that these functions are one-to-one. So what that means is for every y, there's exactly one x. That might not seem important to you yet, but it will when we get to inverses in a couple of sections. So you kind of have to remember that. Now, we know that the definition of a function is for every x, there is exactly one y. Okay? We test that by doing the vertical line test, right? You guys remember the vertical line test, right? I told you that these are exponential functions, which means that anywhere here I could draw a vertical line, and I'm only going to hit that graph one time, right, for all of these, anywhere, okay? Well, one-to-one functions also pass what's called the horizontal line test, right? So they're all functions, they all pass the vertical line test, but for every y there's exactly one x means it's going to pass the horizontal line test. So for example, here's a function, let's use this exponential. Actually, let's just use the linear one. Right, so that's a linear graph, right? And we'll do a quadratic right next to it. Right, that's what a quadratic looks like. Okay, things that we've dealt with before. So the vertical line test obviously works for all these, they're functions. But the horizontal line test, that's what we want to check. All right, so for the first one, right, anywhere you draw a horizontal line, you're only going to run into that graph one time. So it passes the horizontal line test, it is one-to-one. Quadratics, though, right here it works, right? But anywhere else, pretty much, you're going to hit that graph twice. And since you hit that graph more than once, this is not one-to-one, okay? That's a basic understanding of it. I'll go more in depth in class, and we'll talk about it with inverses in section 4, okay? Or maybe 3, I don't know. Last thing is how to solve these exponential equations, okay? So what we're going to do is we're going to express each side of the equation as a power of the same base. We already started working with that last section, how to convert something to look at like it has the same base. Then once you have the same base on each side, you just set the exponents equal to each other, drop the bases, don't even worry about them, because they're not important anymore, they just kind of cancel each other out. Set the exponents to equal to each other, and solve them. Then check your answer. Okay, I'll try to illustrate that with some examples. So we're going to start by just simplifying. We're going to apply all of our rules of exponents that we've talked about over and over again to these weird-looking exponents with real numbers that are not rational. Okay, so we've got 2 to the 4 minus root 5 times 2 to the 1 plus root 5. Can we do anything with this? Yes, you can combine it. The reason we can combine this is because we have the same base. If that was a 2 and that was a 3, we wouldn't be able to do anything with it. Okay, but because they have the same base, you can work with this. So what do you do when you have the same base and you're multiplying? You add the exponents. So keep the base, add the exponents. 4 plus 1 is 5. Negative root 5 plus root 5 is 0. They cancel each other out. So we're left with 2 to the 5th, which we know is 32. Okay, number 2, this is just power to a power. What do you do with a power to a power? Doesn't matter what the base is for this. You multiply the two exponents together. Okay, so we have 5 to the 2 root 3 times root 3. Well, root 3 times root 3 is 3, and 3 times 2 is 6. So 5 to the 6th power, which you could leave as that, or you could plug in a calculator, 5 to the 6th, and you'll get 15,625. I'm pretty happy with either one of those answers. Okay, number 3, what do you do when you're dividing? You got to check, make sure you have the same base. We do. Okay, 3 and 3, so we're good to go. When you have the same base and you're dividing, you're actually going to subtract the exponents. So this is, I'll write this one out because it's a little bit easy to mess up. Keep the base, subtract the exponents. 2 plus root 7 minus 2 plus root 7. Okay? Because we're doing minus this whole thing, which means you distribute that negative, so it's negative 2 and positive root 7. So the 2's are going to cancel each other out, and we've got root 7 plus root 7 is 2 root 7. So 3 to the 2 root 7 power. Now, you could plug that into your calculator and get a decimal answer, but I don't want that. I want the square root. I want the exact answer. Okay, last problem here, number 4. We probably need to write out this way. All right, this one I just snuck in a 5 to the 0 there, so you remember that anything to the 0 power is 1, so that's completely irrelevant, doesn't matter. All right, so we have 5 to the root 3 plus 1 power over 5 to the root 3 power. All right, we have the same base, both 5's. Keep that base, subtract the exponents, root 3 minus root 3 cancels out, so we just have 5 to the first, which is 5. And that's it for those. All right, now let's go to the solving. Okay, this is where you have to be able to manipulate our bases to make them look like each other. Okay, it's a little bit more complicated, but bear with me. Okay, so obviously we see that probably the easiest way to manipulate these two to make them look like each other is to get 2 as our base. Okay, so you got to be able to see that. So we're going to try to get 2 as our base. Well, in order to get 2 as our base on the left side, I'm going to rewrite 4 as 2 squared. So 2 squared, oh gosh, I don't need that parentheses at all. 2 squared to the 2x power. Don't forget about the 2x power. And on the right side, I could rewrite 1/2 as 2 to the negative 1, and that's to the 1 minus 2x power. Okay? So once you get there, we can get our exponents all figured out. So we got power to a power on both sides. So we've got 2 times 2x is 4x on the left side. And you can distribute that negative 1 to get 2 to the 2x minus 1 power. Okay, we've got the same bases. Set the exponents equal to each other. 4x equals 2x minus 1. So 2x equals negative 1. X equals negative 1/2. And that's your final answer. Okay, and then you can plug that back in and check it and make sure you get the right answer. For number 6, okay, same idea. We see that 5 is probably the base that's going to work best for us. So on the left, we're lucky. We don't have to do anything. Just leave it as it is. On the right, 1 over 25 is the same as 5 to the negative 2nd power, right? Because you flip it and you square it. So we need to do power to a power on that side, which means you distribute the negative 2. So we have 5 to the 3x equals 5 to the negative 2x plus 2. All right, we've got the same bases. They're set equal to each other. So we could just drop the bases, set the exponents equal to each other, and we'll have 5x equals 2, x equals 2/5. All right, and number 7. All right, number 7, we need to break down 32 to make it look like 2. So the right side of this equation is fine, 2 to the x. All right, the left side, I'm going to rewrite as 2 to the 5/3 power. Okay, because 2 to the 5th is 32, and that root 3 means that the 3 is in our denominator of our exponent. So this makes it very easy. Got our bases, set the exponents equal to each other. X is 5/3. And the last problem here, we're going to break down, you could break both of them down to get all the way to 2, but you don't have to, right? You could just keep the 4 here and break down the 64 is 4 to the 3rd to the x power. So we'll have 4 to the x minus 2 equals 4 to the 3x, because because we have power to a power, so you're multiplying them, not adding them. Drop the bases, set them equal to each other. We'll have x minus 2 equals 3x, negative 2 equals 2x, x equals negative 1. And that's it for section 2.